you a short overview of IC in artificial intelligence, because it is very important that we know that the classical AI fields where you write the things by your own hands instead of getting the things learned are still there, and they are still important topics. So, and the success with the handwritten and handmade AI, the first success was, of course, with chess winning a game. So all this certainly exists, and it will last even if there are new things coming. And the new things coming are, oops, oh, what is this? No.
Space.
Yeah.
Space.
Okay. So some of the new things are not so new things, also handwritten rules, but what you see is that all these handwritten AI systems can benefit from having things learned, programs and knowledge and whatever, by direct access to the world and not first modeling a digital twin and then working on that twin. No, directly access the world, learn from the world, write it up, or access again. So that is what it is.
Like this. And this, yes.
Aha, because that is.
Exactly.
Okay, thank you.
Thank you very much.
That's the problem. Okay, so everything can become smarter through learning. That is not restricted to artificial intelligence, but also all the fields, the classical fields of artificial intelligence benefit from machine learning, and other fields, of course, as well. Because machine learning is not restricted to be applied to artificial intelligence, but to almost everything. Okay, there had been this conference, ECML Picadilly, with more than 850 participants. That was on learning in Würzburg this year. Okay, so what is machine learning? So machine learning, in my view, and there are very many different views I know, is part of computer science. So it is based on data and therefore has a close link as well to the database community, and therefore we have made the European grassroots conference, ECML Picadilly, a conference that combines the European Conference on Machine Learning and the principles of knowledge discovery and data. Because both together really give the energy to make true applications. And it is, of course, always has a very complex architecture. So machine learning is not just the learning algorithm, that's not it. It is from the acquiring of data, that what I call the access to the real world, until to the deployment that is guiding this. Okay. That is better now, okay. So the whole path is from accessing the true world to get data from it, to learn from it, and then deploy it back to the real world and do some change there. That means action. So it is perception, action, and in the middle there are many, many things. As you can see here, for instance, this is a part of a rapid miner process, a startup from Dortmund that is world leading in data mining currently. And these are embedded processes and very, very long pipelines. So, as you can see on the Stanford Index of AI, the subfields of AI, there you can see that, of course, the classical areas, they all remain. They do not disappear. They are all remaining. And you see that the exponential growth is to machine learning, although it is split here into two different themes, machine learning and probabilistic reasoning on the one hand, and neural networks on the other hand. If you would combine it, the growth would be even more visible. So that's it. So let us come to the very close connections that I personally have with France and French scientists. That is because in Germany, funding of machine learning for decades was not given at all. So we never received any funding until recently. And so we had to combine with the French scientists, particularly with those at LRI Paris, Yves Kodratsov, who had the chair for machine learning already those days, those early days. And so I did already then supervising some PhD students in France, in particular Georges Tecucci, who is now in the US, and Jean-François Puget, who had his very, very successful startup, and then Guillaume Bosque recently. And I also was supervising or reviewing, whatever you call it, habilitations. And so these are just a few scientists with whom I am collaborating already, and you can also see the ecmlpkdd.org website, where there is this grassroots European collaboration on machine learning and principles of data mining. So then some issues of the German AI, where now machine learning is recognized. There is a platform of learning systems, and there are people working in the group technologies and data science, where it is already combined, access to the world, deployment in the world, and machine learning in the middle with all the other things. And there are some nice papers there, and what's next, and so on. And then there are the competence centers, and I'm coordinating those competence centers. There are those for machine learning and big data that are shown here, and there is, of course, the very, very large and distinguished one that is DFKI, and we'll have a presentation on that later on. So, and there are the French AI interdisciplinary institutes, how they are called, and we have a coordinating meeting, which I organized together with Bertrand Braunschweig, and at the ECMLPKD we had this meeting, and we agreed on having mutual visits, curricular coordination, common summer schools, international fellowships, increasing visibility and citation enhancements, coordinated industrial cooperations, and coordinated common European projects and reviewing of European projects. So that was agreed upon, and you can see it also in the common roadmap as Annex 1. There are all these goals that we have developed with the competence centers. Well, then there is, of course, the real event coming next week, which is the Global Forum on AI for Humanity. This is a very important event. It is directly under the patronage of the President of the French Republic, and it is very much driven by what we want to have as the European culture of AI, and that is trustworthy AI, that is governmental regulations for data, that is fighting bias. It is very important to have an impact on labor and society that is for the good, and we want to have the social good in medicine, climate, environment, and other applications. So that is next week here in Paris. And now let's come for something, what I want to bring about is my thesis that ethics for AI requires theoretical insights in AI. It is not sufficient to argue in philosophical and legal terms. It is necessary to know the technical details and have the expertise there. So I think that for machine learning in particular, because it has this exponential growth, and that is that one learning system is programming another learning system that is programming another learning system that is really running in the actual world. Because of all this, it is very, very difficult to explain it. If we could explain it, well, why do our students need 4 years to learn it? I mean, do you think computer scientists are particularly stupid, such that you could explain it to someone in 15 minutes, but these lazy students take 4 years? No, it is because you cannot. I mean, if you explain it shorter, it's wrong. Or to say the least, it's misleading. So we have to think about something, what we can do to make it trustworthy and controllable without just explaining. There must be another way. And so since decades we are talking about it, and now I think we have at least done the first steps. So the one is robust learning. That is, what we need to do is, if there are few changes in the data, there should be only few changes in the outcome of the learning algorithm. Currently, with deep learning, the opposite is the case. I'll show you an example. The other is, what we need is something like transfer learning. That is, if you have learned a model on a subject that is similar to another one, it should be transferred to the other one. That is something which humans find natural. But with our current algorithm, it's not. And so there need to be some research on that. Then, of course, there is learning in hardware. And I'm leading this collaborative research center with 20 professors and 60 PhD students since more than 10 years. And it is about machine learning and hardware. Because very often, there is a nice statistical principle, and then comes the implementation, and then comes a change in hardware, and then things do change. Theoretically, they don't, but practically, they do. And so we have to do a theory that also reflects that. We are working on that. Of course, everything is human-oriented. I mean, that's what we are about. So what can we do with this human-oriented machine learning? We want to have an understanding of the learned models such that they are explainable, interpretable, and inspectable, although you cannot just explain them easily. Then we want to have reproducible results. And that is something which also sounds very natural, but it is not at all given in many cases. And we had long debates at the International Conference on Data Mining in Brussels. We had a night-long debate about reproducible results. If there are so many data as Google have, we cannot reproduce them because we do not have the data. And therefore, we cannot control it. Therefore, we cannot inspect it. And therefore, it might be dangerous or not, whatever. And then we need certification of data and models. And there is some good work on that. And my favorite analogon is this one. You all know this one. And I want to have such things for machine learning. Yeah? And then we can stick them to the algorithms and to applications, and then we can say, look, this is taking so much energy, it is taking so much memory, it is needing a lot of communication, and it is not robust yet, and there is a heuristic, so you are not reproducible, and so on. So that you can have a warning, and then for advertisements, heuristics are well, and for other things like medicine, you should not rely on heuristics, maybe. You can see that. So in a way, what you can do with such a sheet, you can have the understandability and traceability, which starts at the data collection. As I said, it always starts with access to the real world. How is that organized? And then the model of machine learning. And then what is needed, because it doesn't need an explanation, but is a guarantee in such a sheet, is a theory. For the formulas on top, we have a theory. The statistical theory is very good. Then we need an algorithmic theory, and then we need a software engineering theory, and then we need a hardware-specific implementation theory for machine learning. So we need theories at all these levels, and we need insights and proofs there. And then with the proven bounds, we can justify to the user without needing his expertise or her expertise, but we can justify, look here, this is the bound of the error, this is the bound of the bias, this is the bound of the variance, and so this is the bound on the energy consumption or other resource consumptions. And with that, you can then hand over to the user without, but that means that we have to do a lot of research. So in general, we are working on that. The particular problem comes with deep learning, and here are just two examples on that. So what was found was that if you have a deep learning image classification of a guitar and a penguin, and then you do very, very, very small changes to the data, and then you get pictures like these, and the learning algorithm says that this is a guitar and that is a penguin, and you wouldn't do that. So you can imagine that this is truly problem, and there is this nice setup done by Nguyen, Uzinski, and Klum at the Vision Conference. That is a wonderful way you can, using an evolutionary algorithm, you can check how robust your algorithm is. Another, again, with deep learning, because there the theory is not yet as advanced as in probabilistic methods. There we had this example of horse images, and all these horse images came from a website where the photographer was listed there at the left down corner. And therefore, what did the learning do? Whenever there is something in the left down corner, it says it's a horse. So this can happen. You see that by the work of Zamek and Montavon and Müller from the Technische University Berlin. What they did is they made a heat map to show what the learning algorithm is actually using for classification. So that is something which everybody can understand, such that now you can control the model, because then you see, no, I do not consider the left down corner a horse, and you see that is used there, and then you see another model, and then you say, it's a horse with a rider, I would say. Yeah? So you can inspect it, and here you see the trains are classified due to the rails. And then you know, if I want to have rails classified, the learning algorithm is nice. If I really want to have a train viewed as a train, then it is not. And therefore, in this way, the research of Klaus Robert Müller made it visible what actually happens, and therefore you can see that. So coming to fairness, there is a thing, this easy example. Of course, those are captured by police do not look happy. You can see there are 3 examples of criminals and 3 examples of non-criminals, and you see that the criminals look very sad. Yeah, what would you do at the police station if you are captured? Then you don't look happy. Okay, so what does learning do? If someone is looking unhappy, he's a criminal. And of course, we all know that this is not true. So this is about all this bias that comes through the way the data are collected. And statisticians know that for decades. They have a field called planning experiments. And it's good to know that field and apply it. But now currently we use data that are collected for different purposes, and therefore we have all this bias coming into our data. And then there is some bias in the world itself. So as I say, we want to access the world itself, and currently there are not so many women in positions of a CEO. And what happens then is that by the recommendation engine, they never get offered of CEO positions, but of housekeeping, and that's a good thing. So, therefore, our background knowledge is very important. So we need to know whether it would be possible to exist in the world. And there's this nice field in machine learning called counterfactual learning and counterfactual reasoning. That means that things that are not there but could there possibly be are introduced into the probabilistic estimates of the true world. And therefore, you can do different calculations. I just showed here a very easy way of doing it by Francesco Bonchi and colleagues, such that you calculate risk difference for the groups and make it mathematically more balanced, what is not well balanced, but could be by nature well balanced. So we have to understand machine learning in order to give guarantees, and we want to give guarantees to your users such that they know where to rely and where not to rely. And that considers the overall pipeline of the application and all levels of implementation, so down to hardware, please. And then also, we have to control all these libraries. There are investigations currently that the libraries of TensorFlow and Python are not always as they claim to represent, and they actually do something different. Yeah, so you have to take care very much of that. Then we need to be based on theoretical insights of the several disciplines, that is statistics, complexity theory, computer architecture, and application domain. So we have to take into account all these disciplines if we want to give guarantees. And that's my conclusion. Further research is urgently needed.